Alright, so far then we have discussed Kepler's laws, and we talked about how Newton used Kepler and his own thinking and established that Kepler's law of periods could be demonstrated through his thinking, applying his thinking. We then looked at further validating Newton's law by considering the moon, because the moon was a well understood object at that point. So here's another thing that we can do, a common kind of question which you might get. So this is my second example in effect. So let's calculate the mass of the Earth. That's an important thing that we might want to know. So let's consider we have Newton's universal law of gravitation, which is G, some mass on the surface of the Earth, let's say, the mass of the Earth, over the radius of the Earth. And this, of course, this gravitational force of attraction is equal to the weight of this object. So it doesn't matter what the object is, the masses will cancel both sides. So now, sorry, I missed a square there, didn't I? So now we have E, the mass of the Earth, is G r squared over big G. And we know all this. We could measure that. Newton could have measured that. The Greeks did a calculation for the value of r long before Newton, and this is Newton's own constant. So we can stick in our numbers there, and we get 6 times 10 to the 24 kilograms, which is the accepted value for the mass of the Earth, give or take. Let's look at another example. Let's think now about calculating the mean density. Let's call this example 3. Mean density of Earth. Well, we have already established from our previous example that the mass of the Earth is G r squared over G. And we're going to assume that the Earth is a sphere. So that's going to be 4/3 pi r cubed. And of course density is mass over volume. Let's make that mass over volume. So we've got the mass, G r squared over G, divided by the volume. So that's times 3 over 4 pi r cubed. And if we then simplify that, we're going to get 3g over 4 pi r g. And again, we know all these numbers. We're going to get 5,500 kilograms per meter cubed. Now, this isn't just a bit of fun. These are questions you could get asked to do. So be clear as to what I'm doing here. I have made an assumption here that the Earth is a sphere. It's not a bad assumption, but we know the Earth is not a sphere. It is a geoid, or Earth-shaped. And so it is like a sphere, but squished top and bottom. And more of that, and the implications of that later on in the course. So there's our third example. And then we could do a fourth example. Let's get the mass of the Earth using the Moon. So we're going to assume a circular path, circular orbit, because that makes life nice and simple. Don't have to worry about ellipses. We know, of course, the period is 2 pi over omega, which leads us then to omega is 2 pi over t, of course. We know the centripetal force, mr omega squared. And we know that this is the gravitational force. So this is g, mass of the Moon, mass of the Earth, over the radius of the orbit squared. And of course, the mass of the Moon falls out. We rearrange to get the mass of the Earth as the subject, and we get 4 pi squared r cubed over t squared. We know this, we know this, we know this of course, and that'll give us 6.8 times 10 to the 24 kilograms. It's not the same, but it's tolerably close.